Hello, See You Succeed students. This is Dr. Brenzi here, and this is going to be a series of 5 videos on what I'm going to call Unit 10. And Unit 10 is going to be dealing with what is called thermodynamics. So I'm going to call this lesson 10.1, and in this lesson our objective is that we're going to be able to describe the first law of thermodynamics. Now, in thermodynamics, we have 3 laws of thermodynamics. It seems like in physics we have lots of laws coming in sets of 3. And this is no exception to that general rule. So we're going to be able to describe the first law of thermodynamics in words, and then we're going to be able to apply that to solve some physics problems. Now, first of all, what is thermodynamics? Well, it comes from a prefix thermo, which means dealing with heat and temperature. And those are topics that we dealt with in Unit 9 before we started reviewing for the AP test. And dynamics means changing or moving. So if you put those two stems together, or prefix and stem together, you have what's called thermodynamics, and that's the study of how a body's changing internal energy transfers to other forms of energy, and vice versa. So it's basically the exchange of internal energy with other things like mechanical energy, chemical energy, electrical energy. So that's the field of thermodynamics. Now, some everyday examples of thermodynamics. We know that internal energy is it manifests itself in the form of temperature. So if you raise something's temperature, you are raising its internal molecular energy. And so these are like 3 examples of how thermodynamics works in everyday life. You have, like for example, over here on the left, you have the space shuttle, and what's happening is that a chemical reaction is occurring, and that chemical reaction adds heat to a gas, and then that internal energy of that gas causes the gas to be propelled downward. And so that gas now is able to do work on the space shuttle and its boosters, and it will lift the boosters off the ground according to Newton's third law. So that's one example of how internal molecular energy can be transferred to and from other sources. Another example, you go to the movies, you order a bag or a bucket of popcorn. Well, in order to make that popcorn, you have to apply heat to a pan and to some kernels. And what happens is that increases the internal energy of these popcorn kernels. They eventually pop. And when they pop, they end up filling up this can. And when they do that, they're able to actually do work on this lid to lift the lid of the popcorn popper up. So again, we're taking internal energy and we are transferring it to other forms. And of course, you can also say that this internal energy came from an electrical source. And then you have hot air balloons. Okay, hot air balloon works by heating up some air with a chemical reaction, and then that internal energy expands and does work on this balloon. So it fills the balloon, causes the balloon to fill up, and when you have enough air in the balloon, it will actually cause the balloon to rise. So that is yet a third example of how internal energy can be transferred into mechanical energy. And so these are all examples of thermodynamics at work. And that's basically what we study when we work with thermodynamics. So, the basic paradigm, if you will, is you have a system, and this system can be anything. I have a blob. And this blob is separated from its surroundings by a boundary. Okay. And we say that there is some sort of internal energy inside the system. Now, we learned in Unit 9 that internal energy is usually kinetic energy of molecules, but in a real gas, and not simply an ideal gas, you can also have some potential energy coming from interactions between the molecules in the gas, and that contributes to this total internal energy as well. So whether it's a real gas or an ideal gas, it has some sort of internal energy U. And that internal energy in the system can be changed primarily by two ways. We can either add heat to this system, or we can choose to do work on the system. Okay. And when I say work, I'm talking about mechanical work, like squishing this this blob so that you are increasing or decreasing the, well, actually I'll get into more details later, but you could squish this blob or stretch this blob and you are actually doing work on the blob. And so that's the second way that internal energy can be changed. Okay, now a little bit about heat first. Okay, we have a convention in thermodynamics that when you add heat to a system, that system's internal energy increases. Now that is that's not a convention. I mean, that is a fact, right? I mean, we know heat is the transfer of energy, and we give heat a variable letter Q, like I showed on the last slide. And I want to point out that when you add heat to a system, this value of Q is going to be greater than 0. Okay. Now that seems pretty straightforward, just like this fact that when heat is removed from a system, the system's internal energy decreases. Okay, so if this system is placed in contact with a colder body, heat's going to be transferred out of this system, and you're going to decrease the internal energy of this system. Now that seems to be pretty straightforward, right? That this number is less than 0 if heat's removed, the number is greater than 0 if heat is added. But work is trickier. You got to be careful about signs when you're talking about thermodynamics. With work, when the system does work on its surroundings, its internal energy decreases. Okay, so when this actually does mechanical work on the things around it, like say it starts pushing, like say this blob starts pushing on a wall or a let's say, I don't know, maybe I have a little block over here and this thing expands so that it starts to push a little block over here. Well, that means that this system is doing work on its surroundings and therefore its internal energy has to decrease. Now, this is where you have to be careful because when a system does work, the value of W is greater than 0. Okay. Likewise, when work is done on the system, like if we decide to squish this blob, we are doing work on the system and its internal energy increases. But if we want to represent that, the fact that we are doing work on the system, we have to use a value of W less than 0. Okay. Now, it can be tricky to remember that. So the way that I think I try to remember it is by using this scenario here. And let's go back to the popcorn popper. When heat is added to a system, so the system can do work, both Q and W are positive. Okay, so when we add heat to a system, so that system can lift this lid and do work, then both Q and W are greater than 0. Okay. So if you have trouble remembering, is Q positive, is Q negative, remember the popcorn popper. When heat is added, so the system can do work, both Q and W are positive. Okay. Now, how exactly does a system do work? Well, it's primarily by changing its volume. Okay, so if you have if you have a system here, and we're going to say that the system is the bottle and the balloon combined, so that's a combined system right there. So we're going to call this, the entire thing, the system. And if you add heat to this system, well, you're going to increase its internal energy, but this volume expands, and when it expands, it is doing work on the walls of the balloon. So it is doing work on its surroundings. And the way that we calculate that amount of work done is by using this differential equation. We say that an infinitesimal amount of work done is equal to the pressure of the gas times an infinitesimal increase in its volume. And if you were to take the antiderivative of both sides here, you would get the amount of work done is equal to the integral of P dV, beginning at its starting volume, ending at its finishing volume. So if a gas expands a volume so that V2 is greater than V1, it has to do work on its environment. Okay? So if you wonder, gee, is this gas doing work or is this gas having work done on it? Well, if it expands, it's doing the work. One other thing that you have to be very familiar with in thermodynamics is the fact that you're going to see a lot of pressure versus volume graphs in thermodynamics. And the reason that's the case is because our equation that we just derived for work tells us that if we take a graph of pressure versus volume and we find the area under the curve, that is the amount of work that the gas has done. Okay. So we have a couple of pressure versus volume graphs here. Volume, hey, there's volume. And if I take a gas and I hold it at a constant temperature and I increase its volume from this volume to that volume while I am holding its temperature constant, it turns out that pressure becomes a function of volume. In other words, that pressure is going to decrease as the volume increases. So that's why we have to express this as an integral, and we can't simply give it an algebraic form. Okay, so you would have to know what this pressure versus volume curve looks like, or have an expression for it, and then be able to integrate from its beginning volume to its finishing volume, and then the area enclosed in that is the amount of work that the gas does on its environment, on its surroundings. Now, life becomes easier when pressure is kept constant. So you can keep pressure of a gas constant. It's harder to do that, but it is possible. And if you are able to keep pressure constant, then this integral becomes pretty trivial, right? It just becomes work is equal to P times delta V, all right? But that's only if pressure is kept constant, okay? Which in a real system is somewhat difficult to do. So we don't see this a heck of a lot, but except when you're dealing with basic physics problems, because you're just getting used to things. Okay, now that you know about work, now that you know about internal energy, now that you know about heat, and you have a review of what heat is, now I can tell you what the first law of thermodynamics is. Okay, now it says that the change in a system's internal energy equals the heat added to the system minus the work done by the system. And it looks like I forgot to put a W there. Whoop, W. Okay. So, if I add more heat than the amount of work that a system has does on its surroundings, then the internal energy, according to the first law of thermodynamics, has to go up. Okay. Now that might come in the form of raising the temperature of the gas. It also turns out that if you add less heat to a system than the amount of work that it does, then the remaining amount The difference is made up by the fact that you are actually pulling internal energy out of the system in order to do this greater amount of work. Okay. So if you write the first law of thermodynamics this way, you can think of it as internal energy equals heat in minus work out. There's another way to think about thermodynamics and the first law, and that's this way. Heat added to a system changes, heat added to a system, let's cross this out. I just realized I just saw the typo, sorry about that. Okay, so it should read like this. Heat added to a system is split between changing its internal energy and the work it does to its surroundings. So if we add some amount of heat to this system, some of that heat is going to be transferred into raising the internal energy of the system itself. But then there's another portion, and we can't determine that unless we know some other things. Another portion of that is transferred into doing work on its surroundings. So this would involve increasing the volume of the system. Okay. You'll also see your first law of thermodynamics written this way. If we're concerned with infinitesimal changes, like very small changes in heat, very small changes in energy, very small changes in work, then we can write the first law of thermodynamics as a differential equation. And it looks like this. dq, the small change in heat, is equal to the small change in energy, internal energy, plus the small amount of work that is done on the surroundings. And we know that the small amount of work is equal to the pressure times the change in volume. So this is actually another form of the first law of thermodynamics. Hey, that's the same thing. All right. So now that you know the first law of thermodynamics, let me show you an application of that first law. So here's the first law of thermodynamics. Here's how we calculate work. Now, and here is a pressure versus volume graph. And what's happening here is we have a system that starts off at this pressure and this volume. And then what happens is that it will increase in volume to this point. We're going to call that step A. And then it's going to decrease its pressure. Did I say increase pressure here? I meant increase volume here. Sorry. And then it's going to decrease its pressure as we go from here to here. We're going to call that step B. And then the third step in the process is that we're going to decrease the volume. And then finally, we're going to return it to its original state by increasing the pressure in the system. Okay. Now, what I'm trying to do here is I'm trying to figure out the amount of heat that's added. Okay. I'm trying to figure out the total internal energy, and I'm trying to figure out the amount of work that's done. Now, some of this stuff has to be given to me. Okay. Usually this can be calculated because we know we can find work from the pressure versus volume graph, but one of these other two values has to be given to me in order to figure out the other one. Okay. So what I'm going to do for this particular problem is I am going to give the amount of heat added or taken away during each step, and then we're going to calculate the internal energy and the amount of work. Okay. So let's first consider this step where we are taking our system and we are increasing its volume. So step A. So I like to keep a little organizer here. So I have Q, the heat, internal energy, work, and I know that this equals that plus that. Okay. I know that the work is 0 because that is given to me in this particular step. That had to be given to me. The amount of work that's done is the amount of area enclosed by this rectangle here. So that's P times delta V, and it is kept at a pressure of 8 times 10 to the 4 Pascal. And the change in volume is 3 times 10 to the negative 3 cubic meters, excuse me. And when I multiply those two together, I end up with an amount of work equal to 240 joules. So as this thing is expanding, it is doing 240 joules worth of work on its surroundings. Well, according to the first law of thermodynamics, right here, that means that my internal energy has to equal negative 240 joules. So, and because that no heat is added to the system, all of this work that it is doing on its environment, its surroundings, has to come from its internal energy. That's exactly what this is saying. All right, so that's what's happening when it goes, the system goes from here to here on our pressure versus volume graph. Okay, now let's consider step B. So step B is we're going to now take our system and we are going to decrease its pressure without changing its volume. Okay, when we do that, we measure that we have removed 600 joules of heat. So I'm going to put negative 600 joules here in my little organizer. And then I'm going to calculate the amount of work done. Well, it turns out that the change in volume is 0 along this path. So that means that the amount of work that I did, or that, excuse me, the amount of work that the gas is doing on its surroundings has to also be 0. Well, that means that the internal energy also has to equal negative 600 joules. Okay, so again, as I am removing this, as heat is coming out of the system, that has to come from the internal energy of the system. Okay, so now we have step C. So step C is going to take us from this point on our pressure versus volume graph over to here on our pressure versus volume graph. And what I want you to do, I want you to pause the video and I want you to see, or I want you to figure out if you can determine what Q, what delta U, and what W have to be. And when you have an idea of what those might be, unpause the video and I will show you what I came up with. Alright, welcome back. So I assume that you have figured out Q, delta U, and W, and let's see what I came up with. Well, no heat is added to the system during this step, so heat is 0, so Q is 0. The amount of work that's done is actually given by this rectangle down here, because remember, this is the transition I'm making right now. So if I calculate P times delta V, I am actually going to end up with negative 90 joules. Well, remember that when we have negative work, that means that work is being done on the system by its surroundings, as opposed to the system doing work on its surroundings. And then finally, delta U, the internal energy, I have to figure that out from this first law of thermodynamics, and that tells me that the internal energy has to rise by 90 joules. So we are, so as work is being done on the system, it is raising the internal energy of the gas by 90 joules. Okay, now step D. Now, for step D, let's actually add a wrinkle to this. And let's say, okay, how much heat should I add to the system in order to return it to its original state? And when I say its original state, that means that over the entire 4-step cycle, its total energy, internal energy, has to return to what it was before. So that over the entire 4-step cycle, delta U has to equal 0 joules. Okay, now in order to do this, I have to pull some information in from my other 3 steps. So I'm going to supersize my chart here, my organizer, and organize this into 4 different steps, A, B, C, and D. These are all pieces of information that we pulled from previous graphs, or the previous slides, excuse me. Nothing has changed about those. Now, I put 0 joules here because in step D, we are not changing our volume, so therefore we're not doing work, or the system's not doing work. Excuse me, I should be correct there with my pronouns. So over the entire cycle, the total amount of work that I've done is a net 150 joules. And there again, I have to be careful with pronouns. The total amount of work that the system has done on its surroundings is 150 joules. Let's see what I have next here. Okay. Now, because I want to return it to its original state, I know that over the entire cycle, the total internal energy has to equal 0 joules. That has to be given to me in the problem, and it was. So that means that this internal energy for step D has to be such that all of these 4 add up to 0. And it turns out when you do the math, if I add 750 joules of internal energy in this last step, D, that will return me back to my original state. So that's actually the answer to the first part of the question, if I remember correctly, is that how much work has to be done. All right. Well, actually, no, I didn't actually give that, did I? But anyway, now we know how much internal energy has to increase. Well, according to the first law of thermodynamics, that also means that the amount of heat that is added to the system has to be 750 joules, because this has to equal that plus that. So if I need to raise the internal energy of the system 750 joules so that it gets back to its original state, then I have to add 750 joules of heat during this step D in the process. Whoops, during step D in the process. Okay, well, there's one blank to fill in, and that is how much net heat do I have to add over this entire 4-cycle period, or 4-step cycle, excuse me. Well, it turns out that the total of all 4 of these columns, you can figure that out, it's 150 joules, right? Well, if I just look at the totals here, I notice that this also obeys the first law of thermodynamics for the entire cycle. Q equals delta U plus W. Okay, interesting. So not only does this work for a single step, but this works for entire cycles, entire thermal cycles, where you're starting here and you're coming back around to where you started off. Interesting. All right. Well, what if you were given a problem like this instead? Let's consider the same system, same pressure versus volume graph. The same constraints. In other words, I want to return back to my original state so that the change in internal energy is equal to 0. Do I have to actually look at each of these 4 individual steps to figure out how much work it does and how much heat is required to do this work? The answer is no, I don't need to actually do that. I can actually take a little bit of shortcut, and here's what the shortcut is. If I want to figure out the amount of work that a system does in a cycle like this, a closed cycle, I can actually just figure out what is the enclosed area. Oh, and I forgot to say, hey, this is 0, right? Because that's what it means to return it to its original state. All right, back to work. And I mean work in W sense. All right, I just told you I can actually figure out the amount of work that this does in one cycle by actually figuring out the area of this enclosed area. So the amount of work that's done in an entire cycle is equal to this enclosed area. Now, if you're not convinced of that, let's quickly go through it. Remember, in step A, the amount of work that was done was this big rectangle, okay? And that was positive work done. Now, when we came down to step C, we did negative amount of work, but that negative amount of work was equal to this area right here. So if I want to figure out the net amount of work that it does over the entire cycle, I take this big area, minus this small area. Well, and I'm left with the area that's enclosed by the cycle itself. Well, let's calculate what that is. We know that this difference is 5 times 10 to the 4 Pascal. This, well, that's not Pascal, is it? So I better erase that. It's the difference of volume is 3 times 10 to the negative 3 cubic meters. Get my units right. And when I multiply those two numbers together, I end up with 150 joules. So, over the entire cycle, this has done 150 joules of work. Well, that happens to exactly match the analysis that I did on the last slide, where I took each step one by one by one by one and then added them all together, and I came up with a net work of 150 joules. Well, we can use the first law of thermodynamics to figure out how much heat is required to do this work. Well, we know that that work has to be 150 joules. Okay. Now, one other thing I noticed popped up on my slides that I need to talk to you about. That is when I calculated this amount of work by using this enclosed area, how did I know that this work was positive and not negative? Well, here's what you have to do. Remember that when volume increases, work is positive. When volume increases, the system is doing work to its environment, so that work is positive. Okay, well, this is going to be a large positive number on this step, a large positive work. It's going to be a smaller negative work as it goes from here to here in the cycle. Well, the positive work is larger than the negative work, so I know that my net work that I do over the entire cycle has to be a positive number. Now, what if I had an enclosed system that went something like this? If it goes in the other direction, then what happens is volume is decreasing up here on top, which means that is a large negative amount of work. Down here, work is increasing, or volume is increasing, excuse me, so that is a smaller amount of positive work. So in this particular case, if the cycle were going in this direction, the amount of work would actually be less than 0. So we would have to do a net amount of work on the system from its surroundings. Okay, ladies and gents, I know this has been a long video, and I know I've covered a lot, but I really had to establish a good base with a good understanding of thermodynamics, because if I don't do that, a lot of the stuff that I'm going to teach you throughout this mini unit is going to be confusing to you. So, longer video. Hopefully the videos will shorten tomorrow. Along with this video, I've posted a couple of problems that I want you to practice if you have time and the inclination to do so. Again, I think they're going to be really helpful for you. I think thermodynamics is a cool and important part of understanding physics. And so I'll leave you with that, and look forward to talking to you again soon. Bye.